Today we'll be covering the last chapter of Unit 3, which is sound. So that's chapter 3.4. So hopefully you recall everything we've talked about waves so far. And so
Yeah,
sound is basically a type of wave. And as we mentioned earlier, sound waves are actually longitudinal waves. Right, so unlike electromagnetic waves or light waves, which are transverse, so this is what they look like. Longitudinal waves, right, travel differently. So they travel at in the same like the uh, energy or the particles move in the same direction as the wave is moving, and so what you get are areas where they're uh, the particles are close together, and then areas where the particles are far apart. Now, why am I saying particles are close together or particles are far apart? Right, is because longitudinal waves require a material medium to travel. Right, unlike light and electromagnetic waves, which can travel through vacuum where there's no matter, right, longitudinal waves, which include sound waves, need matter to travel. And so, in the traveling through matter, the particles that matter sort of compress together, they come together, and so those regions are called compressions. As we This is something we've covered earlier, but still. And then the regions where the particles are further apart are called rarefactions. Right, now, as far as the properties of waves are concerned, sound waves have all the properties of waves, right? So they have wavelength. So the distance between two consecutive compressions or two consecutive rarefactions is the wavelength, or lambda, as the symbol. They have velocity, right? They have frequency. So just as a recall, frequency is the number of waves completed per second. Right, wavelength is the distance between two consecutive compressions or rarefactions in the case of longitudinal waves. And then velocity, so the longitudinal waves follow the wave equation, which is v equals to f lambda, which is frequency times wavelength. Right, so all of those properties of waves follow. And also, right, sound waves, right, uh, carry and transfer energy. And because of that, they're actually called progressive longitudinal waves. Longitudinal waves. Now, as far as requiring a material medium, right, so an experiment conducted where they put like a bell, so a bell with like a hammer, right, and the hammer strikes the bell. And what they did is that they put it in a jar where there was vacuum, so there was no air inside. And then they switched on the bell. So the bell was like the hammer striking the bell, but you couldn't hear it. Why couldn't you hear it? Because there was vacuum inside the jar, and so the sound wasn't able to travel outside. And so that experiment proves that sound waves, these longitudinal waves, they need material to pass, right, to travel. And right? It's not just air, but they can travel through, right, air, which is, an example of gases, but they can also travel through liquids and solids. In fact, they travel fastest with solids, then less so, right? So they travel at whatever, like the speed of sound through air is, just look it up, just give me a second, 330 to 350 meter per second. Right, it's obviously much less than light, but just for a comparison, in water it's 1400 meter per second. Right, so liquid, as in we're talking about water, and in solids, like it's sort of a little bit in like concrete, right? So the cement and everything, it's 5000 meter per second. So, right, this shows us that not only does it require medium, but why is it traveling faster in solids and then less so in liquids? Because all of this is matter, yes, but there's more matter in solids, it's closer together, right? And so, right, in liquids it's further apart, and in gases we know it's all over the place. Now, why does it need matter? That's the question, right? the, and that is because sound waves are actually caused due to vibrations, right? So sound waves are caused due to vibrations. And so for vibrations to happen, you need matter, you need particles, right? If there are no particles to vibrate, if there's no matter to vibrate, then sound is not going to travel, right? And so, and the more particles and the closer together they are, we can understand why sound travels the fastest in solids and then less so in liquids and less so in air, because you have the particles but they're further apart. So the vibration transfer is like slower. So the speed slows down. Does this make sense?
Yes.
Okay, and
Yes.
so the beating of a drum, the skin of the drum vibrates and that produces the sound, or a guitar, so the strings on the guitar vibrate and that produces a sound. And so any object that's producing a sound is basically vibrating. And to sort of hit that message home, right, for a speaker, right, like if you got like a decent sized speaker, they have something that's called the diaphragm, which is this round disc type thing you can see in it. Have you ever seen this? Right, it's normally behind like this mesh. Have you ever seen this?
I think I have.
Right, so this is your speaker and you've got these diaphragms on it.
Yeah.
Right, and so what happens is the diaphragm, right, so if this is like a side view of the diaphragm, right, what happens is it moves forward, so it sort of bulges out, and what that does is it pushes the air closer, so that causes a compression. Then it sort of goes back, it thins, right? So it causes like it makes space between the air particles, and that causes the rarefaction. And so basically what it's doing is it's like sort of pushing the particles together and then moving back, so it's causing a space to be created. And so that wave is being transferred, that vibration is being transferred through the air, and that's what sound waves are, like in this case, or any case in fact. So those vibrations of different instruments are transferred to the particles of the, and we're saying air because that's basically how, right, it travels. But an interesting thing is, like, an example of sound traveling through solids. Have you ever made like a telephone at home? You have you?
With the cup?
Yep.
Yeah.
Aram, have you?
Yeah.
Right. So what do you do? Right. You speak in here, and you've got the string, and the string needs to be stretched out. The reason why it needs to be stretched out is so that the vibrations can travel right on the stretched string. If it's not stretched, the vibrations don't travel as well, right? And so you speak over here, and the guy on the other end can listen to you very quickly. Why? In this case, the sound is traveling through solid. String is a solid, right? It's not
Yeah.
traveling. It's being spoken into the cup, and then through the string, and then and so that again tells you it needs material. It travels faster through solids and everything that we've been talking about up till this point. Any questions?
No.
No.
Okay, good. Uh, okay, then if that's clear, then you're making good progress. What are the limits of audibility for humans? So limits of audibility. The ears can detect sounds ranging from 20 hertz, so that's the frequency, remember, to 20,000 hertz. That is the upper limit. So obviously the lower limit and the upper limit. This is the limit of audibility. Anything below 20 hertz or anything above 20 hertz, and the human ear cannot detect it. And it will not even register that there's something, that there's some sound that is above 20,000. If it's above 20,000, we can't hear it. Right? Have you, do you know about the dog whistle? Like there's a whistle which you blow, which you can't really hear, but dogs come running when they hear it, like if they've been trained to.
I have heard of it.
No.
I heard the name of it, but not in real life. Like I have experience.
Right? So what a dog whistle does when you blow into it, like what a regular whistle is, right?
Yeah.
A dog whistle is made such when you blow into it, it actually emits in, right, ultra, like the upper limit, right? Anything above the upper limit, sound above, okay, what am I writing? Sound above the upper limit is called ultrasound. Does it sound familiar?
Yeah. I think. Yeah.
Yeah.
Right? You might have heard of it in terms of medical procedures.
Yeah.
Right? And it is exactly what it says. It's ultrasounds, right? So the frequency that they're using is above 20,000 hertz. So dog whistles use ultrasound. Dogs are able to hear it, right?
Mm.
Bats use ultrasound. So when they scream, we can't hear it, right? We can just hear the squeaking, but they're actually making like a lot of noise, right? But all of that noise that they're making is using ultrasound. We can't hear what they're saying. I mean, we are not like saying, but the noise that they're making.
Hmm. Okay.
Right, so ultrasound does exist all around us, and infrasound as well, right? So maybe the noise that insects are making, we can't hear those. It's a very very low frequency, but it's not like they aren't making noise. Okay,
Yeah.
now we'll get to uh, what you call it. We've talked about the speed of sound, right? And we'll talk about ultrasound later. So now let's talk about reflection of sound and echo. So as I mentioned, because sounds are waves, then everything that we've talked about waves so far, we've talked about the refraction and diffraction and reflection and all of that, it applies to sounds as well, right? Now, obviously, sound passing through a glass will bend and all of that. We're not talking about that, but it does happen with sound as well, right? Right. And so what we're talking about right now is the reflection of sound. So when right sound waves are reflected from hard flat surfaces, they sort of bounce back, and when they bounce back and when they reach you, right, you can hear it because it's sound, like just like you can see light coming back from, like it's reflected from a mirror and you can see that. When sound is reflected back, you can hear it again, and that's what an echo is, right? So an echo is the reflection of a sound wave. All right.
Yes.
Okay. Now, something called reverberation. So what happens is that if the distance between the source of the sound and the surface from where the sound is reflecting is uh, 15 meters or closer, right? So if the reflecting surface is 15 meters or closer to the source of the sound, right? What happens is that the echo joins or merges with the source, and that causes what is called a reverberation, right? So the sound sort of mixes together and you can sort of feel this vibration happening. Okay, so this is something that is made use in perhaps theaters and concert halls and auditoriums, where the speakers are positioned such that the sound from the speakers reflects from the walls and comes back, and so it seems louder, right? And there's sort of that
Yeah.
echo and loudness, instead of, like, if it's not happening, then even though the person speaking, it doesn't, like, it seems sort of like flat and quiet and the sound doesn't come right, right, which is called like dead, right? The dead spots in the hall.
Hmm.
Now, right now, it's just something that you need to know, that reverberations happen, right? And they happen when you're 15 meters or closer, right? The source is that much close to the reflecting surface, and so the echo merges or joins with the original sound. Okay, now measuring the speed of sound. Now that we know about echo, there are two ways of doing this. Right, the first method is called the echo method. And so what they're going to do is they are going to uh, right stand, like they're saying stand about 100 meters away from a high wall. Right, so the distance between you or the source, and why are you the source, we'll see, right? And the reflecting surface, right, is 100 meters. Now, why are you the source? Because you're going to clap, right? And when you start clapping, what you're going to do is you're going to adjust the rate of your clapping. Now, every time you clap, you're going to hear an echo. But what you want to do is you want to adjust the rate of your clapping so that the echo, right, joins with each new clap. Okay. So each clap coincides with the echo, and the echo is from the previous one, right? Because it's going and coming back. So the echo of the previous clap is merging or coinciding, or right, with the new clap. Now, when that happens, you want to maintain that clapping rate for 30 seconds, right? When you have that rate, what's happening is that the sound has traveled, right? At this rate, the sound from one clap travels to this reflecting surface and back in the time period between one clap. Does this make sense?
Yeah.
Did you say something?
No.
Okay, I think like something's going on because I can just hear like a very, very muffled sound. Anyway, so, right, for example, I go, so the time it took me from one clap to the other, when I reach the second clap, the echo, which I'm not getting any echo right now, but when I go the second time, the echo from the first clap has, I can hear it exactly when I clap the second time. And right, that means that the sound wave from the first clap traveled 100 meters one way and then came back, so that's 200 meters. So it traveled 200 meters in that much time. Now what I want to do is I want to maintain that rate of clapping for about 30 seconds, right? So I'm going to time 30 seconds, right? And I, right, know the distance between the wall and myself, obviously, right? So the distance is known. And so what I'm going to do is, right, the speed of the sound wave is twice the distance because the sound wave from the clap is going to the wall and then coming back. So it's covering double the distance, right? And divided by time. Speed is distance over time. And whatever value I get from that, right, is, uh, in fact, no, let me correct that. I'm not going to time, so right, sort of a mix up on my end. I'm not going to time 30 seconds, but I'm going to time 30 intervals. So basically, when I reach this rate of clapping, I'm going to time myself for 30 more claps, basically, right? So this perhaps takes me like a minute and a half or whatever. So that is the time. I know the distance, and that will give me the speed. So it's 30 intervals of clapping, not 30 seconds, right? So that's a correction. This is one method called the echo method of calculating the speed of sound. Okay,
Yes.
Hara?
Yes.
Okay. The other method is called the direct method. So it's straightforward. What you do is you have a source for the sound, and you've got two microphones, right? So ice cream cones, you've got two microphones, you've got the source, and these microphones are attached to a computer, right? And so you produce a sound, and you know what the distance is between the two microphones. And so when you produce a sound, when it reaches the first microphone, you get a signal on the computer screen, and then when it travels and reaches the second microphone, you get another signal on the on the computer screen. And what you do is you note the time it took, right, for the two signals to appear, right? So difference between the time it took between the first and the second signal, right? That's the time it took for the sound to travel between the first mic and the second mic. And then you simply do v equals to d over t, right? Velocity is, or speed is, distance over time. Okay,
Uh,
so obviously that is a much easier method, but then you need the microphones and the computer and the setup and everything. Now this method can also, as they say, can be used to measure the speed of sound in different materials. For example, I want to measure the speed of sound through a metal bar. So what I do is, between the two microphones I place a metal bar. So the right when the sound is detected by the microphone, it goes forward through the metal bar and then to the second microphone, right? And so that way I can detect, for example, the speed of sound through that metal bar. So that the experiment can be uh, changed and adjusted as per requirement. Okay, any questions?
okay. No.
No.
Okay, now some sort of properties of sound or sound waves. So they start off by talking about musical notes. What they say is, what's the difference between the sound produced by a guitar or a trumpet or a drum as opposed to the sound of, you know, someone hammering a nail into the wall, or, writing on a chalkboard, or the sound from a car engine, right? What differentiates the sound of music from the sound of noise? Okay, and so what they say is, if the vibrations that are producing the sound are irregular, then they're going to produce noise, right? So it's not pleasant. There is sound, but it's not pleasant to hear. Whereas if the vibrations are regular, then those are musical, right? They can produce musical notes. Now, for example, someone's hammering a nail into the wall at regular intervals, so the sound produced is regular, but it's not something that you'll call music. But given that it's happening on it's a regularly produced sound, you can sort of knock on the door and hammer a nail into the wall, and sort of the sound of maybe a cloth rubbing against your table surface when you're cleaning it, And so you can sort of mix those sounds if they're all regular sounds and make like, ad hoc music. And people do that, like they use trash cans and mops and, opening and closing the window and opening and closing the door. If those produce regular patterns, then it, mix them together and you'll get some, some form of music. But musical instruments, as we mentioned, like the drum and the guitar and the piano and everything, so they produce regular sounds and those can produce musical notes. So what are the qualities or the properties of sound in this case? So there are three of them. There's pitch, there is loudness, and there is quality. So first let's talk about pitch. Right? The pitch of sound depends on the frequency of the sound wave. So frequency again is the number of complete waves per second. Right? So depending on how many waves per second you have, that's what is called the pitch of a sound, right? And just for comparison, right, it is the frequency of light that gives color. So pitch in terms of, it's like the color of sound. So they give the example of musical notes. I am not familiar with those, but they say, for example, a middle C is, right, 256 hertz, whereas a high C, upper C, sorry, not high C, is 512 hertz. And so the way that would sound would obviously be different. Okay, so that is the pitch. Now, they give the example of a tuning fork. Tuning forks are an instrument that are designed to have, like, they can have fixed frequencies or they can be adjustable as well. And different pitches, different frequencies can also be generated through speakers, right? That can be adjusted to a certain frequency. So right, let me share a video of a tuning fork that I pulled up earlier. Hopefully, right, it works. Let me put that on screen. Now they've got like chakras and stuff, and I don't know. So the one I actually pulled up was this one. This is talking about resonance, which is not...
The demonstration we're talking about today is resonance. What happens when an object is forced to vibrate at its natural frequency? This tuning...
What I want you to focus on is the sound that the tuning fork makes, right? The resonance and everything they're talking about is not relevant to us.
Tuning fork has a natural frequency of 256 hertz, and this tuning fork is adjustable. Right now, it's set to 256 hertz as well. When I hit this tuning fork and point the boxes at each other, the sound waves from this tuning fork will cause this box to vibrate. When that box vibrates, it makes the tuning fork vibrate. So when I do this, I'm going to hit this tuning fork.
And so that sound you heard, that is the 256 hertz frequency. Now what you're going to see next is an example of how energy is transferred via sound waves, right? It's transferring to the box next to it, and even though he did not hit the other tuning fork, it's going to start vibrating as well.
But you can still hear it vibrating. A lot of
Right, so he put his hand on the one that he hit, and that stopped the vibrations of that tuning fork. But when he hit it and the sound waves that were generated at that frequency, they traveled to the box next to it, and it started vibrating. Right, and so that's why you could still hear the tuning fork, humming.
A lot of times people think it's the original tuning fork still making noise, but it's the other one.
Right, so that's just an example of tuning fork. There's probably a better video out there. I wasn't able to get one. I mean, find one with the time I had. If I do, then right, I will share it with you later. So that's just an example of a tuning fork, which is an instrument that has, can have a fixed frequency or can be adjustable, having different frequencies. The next, right, how much time do we have? We have about 15 minutes. Okay. So the next quality of sound, or well, property of sound, is loudness. And so why do we feel some sounds are loud and some are low? So this does not have to do with frequency, right? Frequency is different. We just talked about, frequency to do with, pitch. Loudness has to do with amplitude. On the amplitude of sound wave. So recall, right, for a transverse wave, right, this is one wave, and then this is another wave, right? You can see that it's going higher and lower. So the first wave has lower amplitude, the second wave, it's following like the wavelength and the frequency is the same, but the height of the crest and the trough, right, is different. And so that's what amplitude is. So the same concept for sound waves. So sound waves having higher amplitude are louder. Why? Because they have more vibrations and therefore they've got more energy, right? So higher the amplitude, right, which means more vibrations, which means more energy, right, which means the sound is louder. And finally, right, the quality. Quality of sound. The quality of sound is also called the timbre. Right, and this is, right, how sort of clean the sound is. And to explain this, what they say is that, for example, you are producing a sound of a frequency, right, using different instruments. So you're using a tuning fork, and then you're using a piano, and then you're using a violin. And right, you're producing the same type of sound, the same note, so the same pitch and everything from these three different instruments. And you are recording the sound on a screen. Now on a screen, it's going to appear like a transverse wave, but it's not actually transverse, right? So it's going to appear like this. And so what happens is, right, for a tuning fork, it's a very clean wave, right? This is called a sine wave. For a piano,
Does,
hmm?
for the quality sound, does it mean how clearly you can hear that sound?
Yes, how clean that sound is at that particular frequency,
Okay.
right? For a piano, it's sort of like this. So it follows the same frequency, it has the same frequency and amplitude, right? But it has like other frequencies mixed in. And for a violin, it's even more. It's like, now obviously it's better represented in the text, but just to give you an example. So in principle, all three of these are the same, but this is just one frequency. It's very clean. And right, these have other frequencies mixed in. Right, and so the quality, the higher the quality, means you can clearly make out that particular frequency. It's not mixed with something else, right? So obviously, other than a tuning fork and something called like a signal generator, right? So an electronic signal generator, those are the only devices that produce really high quality clean sound, okay, or pure sound, okay. Now, any questions?
No.
Okay, so uh, I'm going to take you to the book for the last bit to complete this chapter. That's just, a bit of reading. So here you can see, right, the topic of ultrasound, which I mentioned that we'll come to later. So ultrasound is anything with a frequency higher than 20 kilohertz or 20,000 hertz, and it can be electronically generated and displayed on a device called the cathode ray oscilloscope, right over here, cathode ray oscilloscope, also called the CRO. And it can be produced by sending an electrical signal to something called a quartz crystal, sorry. And that electrical signal causes the quartz crystal to oscillate, which causes vibrations, which sends out that frequency. And it can be detected by a different or perhaps the same quartz crystal, and then it works in the opposite way, right? When it detects those vibrations, first the vibrations were produced by an electrical input, so electrical input to the crystal, which caused vibrations. Now the vibrations are picked up by the crystal and they are converted to an electrical signal, which is displayed on a screen. Okay, so right, this is the basis of ultrasound. Now, ultrasound is used in different scenarios in life. So one is sonar imaging, right? Bats use sonar, they emit ultrasound, and when it reflects and comes back, they can hear it, and they, from that echo, they sort of may make a judgment of if there's any object to avoid, or if there's any, insects to eat or fruit or whatever it is that they are looking for. Ships use sonar, so right, there's a transmitter, they send it down, and right, they can use it to determine the depth of the seabed or to find fish, right? And so what they do is they send down ultrasound, and then when it's reflected, there's a receiver, and then whatever, information they get from it. Motion sensors also work on the same principle. And then ultrasound imaging in medical, checkups. So what they're doing is that they're using ultrasound on a mother to check the health and growth of the baby in the womb. And right? So it's scanned over the mother's abdomen, and the device that they're using is a transmitter and receiver as well. And when the ultrasound is reflected, when it hits the fetus or the baby in the womb and it's received, the reflections are picked up and they show up on the screen to give you an image like that. Now, this is a colored image. Normally, we see black and white. So reflection of the ultrasounds occur from the bodies of the soft tissue and the bone, so that images even of internal organs can be obtained if required, right? It is not as far as bones are concerned, the detail is less than x-rays, but then x-rays we know can be harmful. Ultrasound is not harmful, right? So you're not getting as much detail of bone, right? X-rays can't pick up soft tissue like organs. So if you take an x-ray, you can't see your stomach, you can't see your lungs as such, right? Well, technically you can see your lungs, like what's in there and all that, but that's a separate matter. So, right, ultrasound is safer than x-rays. And right, why? Because it has a much longer wavelength as compared to x-rays, right? The wavelength of ultrasound is about 1 millimeter, so it is not harmful to humans. And other uses, ultrasound can be used to clean jewelry and other objects, and that's it. So right, this is just stuff that you need to read and sort of like, okay, fine, this happens. Any questions?
No.
No.
Okay, so with that, we are done with the unit of waves. This was the last chapter. And right, so the next unit, section 4, is electricity and magnetism. All right, so I'll see you guys, next time.
Okay, Allah Hafiz.
Allah Hafiz.